Bonjour. Добрый день. We are going to start the program with some technical announcements. And let me introduce you for those who don't know him. It's Martin Stepniczka, who's going to give these announcements.
Thank you very much, Bernard. So, good morning after the heavy Spanish night. I hope you enjoyed, but we have to go on with the scientific program and not only scientific program. So I dare to take 5 minutes at the beginning of this plenary lecture, which I'm very much looking forward to a little bit grab your attention and to mention a few technical details. We'll talk about football match details. These are the teams we have composed. The first is a team of organizers. As you can see, it's purely composed of people from Ostrava and Košice plus family members. So when playing football, please be careful because of kids. And the second team is a team of participants, which you can see is highly internationally consisting of people from all over the world. But let me point out one special case, which is Lubomir Antoni, who's also from Košice, but he explicitly expressed his willingness to be a goalkeeper of the other team. I don't know what it means, if it means that we have an agent in the other team, but your will is respected, so you play in the other team. So this is how it is. But more importantly, there are two extremely important persons in both teams. These are very brave captains that deserve our applause, Zahra Alijani and Shivani Singh. And because we dislike separating the world into groups like organizers and the rest of the world, since now it's Team Zahra and Team Shivani. So these are the teams that will play football. There are also other important persons behind the football match. Cheerleaders. They always make the atmosphere that is simply unforgettable. And the leader of the cheerleaders is Stelka. So if you want to join, if you haven't joined cheerleaders and you want to join cheerleaders, please ask Stelka. And if you don't want to join, Stella will find you anyhow. And another important person behind every football match is a referee. Not just a referee, it's an almighty referee. It's always fair play promoting referee. And it's an incorruptible referee. So Michal Baczynski, thank you very much for being who you are. Team Zahara is already winning 2-0 at the moment, right? And some match details, please, just not to forget. We have 2 half times, 15 minutes each. We play penalties after the match. Small goals, no goalkeepers. That's small goals, so it's very difficult to aim precisely. Scores on the match and penalties are summed up, so even if the team is losing at the end of the match, nothing is lost. And volunteer penalty competition between the halves is always taking part of the match. So you can win some award, like Manuel won, I think 2 years ago. Players, please come 20 minutes before the warm-up, because we don't want to have any injuries. And spectators dress well, like, take a look at Manuel's cap. It's really cold, it's really chilled out. Thank you very much for your attention. Enjoy. Just, if you don't know where to go, it's just the second floor to the corridor, and enjoy the game. Thank you.
Thank you, Martin. As Martin said, we have to go on with the science. And it's a pleasure this morning to introduce Agnès Rico. She's an associate professor at the Université Claude Bernard in Lyon. And in 2024-2025, she obtained a research position at the CNRS, and she's associated with the laboratory we all know, LIPSIS, at the Sorbonne University. Her research focuses on non-classical fuzzy integrals used in decision theory. We heard a lot about them already at the conference. Choquet integrals, Sugeno integrals, and the many variants that we have of them. She works on their axiomatization, elicitation, interpretation, and applications, especially in a field that is quite hot at the moment, XAI. So if you have people in your team or among colleagues working on SHAP just get angry like me. They're not being very respectful to a person called Shapley. And these SHAP values are precisely the coefficients of the linear approximation of the Choquet integral. So I think our community has a lot to say when it comes to interpretability and explainability. And I'm looking forward to learn a lot about that from Agnes. But I just want to thank you before also for giving a hand or two hands or more sometimes at Fuzzy Sets and Systems, because she's also an area editor of the topic aggregation operators. Thank you very much for that. Okay, let's welcome Agnes.
Okay. Okay, thank you, Bernard, and thank you, Martin, to invite me in this beautiful conference. So I'm going to speak about integral explanation. So this is a work I made with two collaboration. The first collaboration, the oldest one, is with Didier and Henri at Toulouse. We work on qualitative integrals, which are variants of Sugeno integrals. And last year, I have a collaboration with Lipsis, with Christophe and Marie-Jeanne. And they are experts in explainable artificial intelligence. So I put together qualitative integrals and explainable artificial intelligence, and this is the subject of my talk. So the aim of this talk is to explain how I use Gödel integrals for knowledge integration in XAY. And no. And I would also explain you how I can elicit Gödel integrals in this context under uncertainty. So for this, I will speak about qualitative representation and then qualitative integrals to focus on the famous one in this talk. This is Gödel integrals. I will briefly then explain how I made representation data in qualitative context. Let's go to the motivation to qualitative context, because qualitative representation is well aligned with human reasoning, and this representation supports reasoning with limited data. So one challenge for qualitative representation is to stay in qualitative context from the information provided by experts and the interpretation given to user. And we want to do this without going to numerical context. So I participate to this challenge considering objects evaluated according to many features and evaluated on qualitative data, and especially totally ordered set. So I participate to the challenge with qualitative aggregation functions. So in this talk, I will speak about Sugeno integral and qualitative integrals. They are defined using capacity to represent the weight of subset of criteria and interaction between them. So capacities appear in 1950 to generalize probability, and there are some tools and famous integrals named Choquet integrals presented yesterday. And in qualitative context, many authors define similar tools. So possibility from Zadeh and the theory of possibility from Didier and Henri. And the famous qualitative integrals is Sugeno integrals. I have an honor to work with him, so very nice person and very great researcher. So Sugeno integrals was defined by him during his PhD study. I was 1 year old. Yeah. So let's go to qualitative integrals to present them. So I consider a finite set. This will be a set of criteria if I play in multi-criteria decision making, or it is a state of nature if I play in decision under uncertainty. I have a weighting scale. This is, for this talk, this is an order structure with a top element and a bottom one. And I have an evolutive negation and also the minimum and the maximum. An object is represented by a vector, and each coordinate is its local evaluation. And I consider qualitative capacity. They are set function increasing and with the condition 0 for empty set and 1 for all the sets. To reduce the complexity due to the capacity, because you need to have 2 power n elements, we always use Möbius transform. And Möbius transform only keep essential elements for the capacity. So they have the Möbius transform is equal to the capacity if there is no subset with a capacity equals. Otherwise, it turns to 0. So Sugeno integrals is based on a min-max equations. So they compute a global evaluation, and they have many. Sugeno integrals has got many equivalently expressions, and we can take the first one. For example, we take the minimum of the capacity and the minimum of the value on the set, and then the maximum for all the subsets. And we just need to use the focal elements. But to define qualitative integrals, we notice that Sugeno integral has expression in using the Klein-Dienz conjunction and the Klein-Dienz implication. There is an equality for both expression, and with qualitative integrals, we are going to also define 2 expressions, one for conjunction, one for implication, and they are linking with semi-duality, but we lose this equality. You also see that when you look at the expression of Sugeno integrals, we take the minimum of the capacity and the minimum of the value. So we reduce the scale for the top and the bottom, and the score given by Sugeno integral may be an element in the vector, or maybe an a value of the capacity. We can have both. So now we change for conjunction and implication linked by semi-duality, and we obtain conjunction-based qualitative integral and implication-based qualitative integral, and they are not the same. We work in a totally ordered set because we want to use the knowledge of user. So it's important to be simple for the request. And further explains that when we play on a finite totally ordered set, we start with the minimum and the implication of clean-ins. And we use with residuation and semi-duality, and we turn in this square, and we obtain Gödel implication and Gödel conjunction on the right, and they are linked by semi-duality. So we already know many particular cases of qualitative integrals. So if we consider for conjunctions the product, we obtain Shigret integrals, also found by Kaufman. Other one, we can also cite triangular norm for conjunction, and we obtain Sugeno-like integrals from Grabish. And semicopola, also, we can find work with Borzova, Molnarova, and co-authors. And if we use a commutative monoid and complete residuated lattice, we can think about the work of Michael and Edward Jack. So in this, for these qualitative integrals, we have dual relationships, and there is a difference because the conjunction-based integral is different from the implicative-based integrals. It is important, so I say this thing twice. So Grabish and co-author notice this inequality for T-norms, different than mean. Recently, Bogzet and Kalu's case, sorry for the pronunciation, studies the set of the conjunction that satisfy this equality, and they prove that we have only conjunction which are composed by minimum and function on the qualitative scale. So now I focus on Gödel integrals because it is the famous one in this talk. So we have two integrals. The first one is implication-based conjunction integrals. And the Gödel conjunction of two elements is 1 if the left part is lower than the right part, and beta otherwise. So first, we may note that Gödel integrals evaluates the vector, but it gives an element present in this vector. It is not the capacity value to be obtained for evaluation. So if you look at what is in the expression, we notice that the vector is selected to 1 if in each focal set of the capacity there is one value large enough. And the larger is this focal set, the more demanding is this Gödel integral to turn into 1. So I present you an example for 3 criteria and the scale. And I just give you the focal sets, but because it is not, you can do just this to compute the Gödel integrals. So I propose you a first element equal to 1 because in each focal set there is one value large enough. The second one is 0 because it is not the case, and the value is 0 for a focal element with a capacity not equal to 0. For a conjunction-based Gödel integral, we have the conjunction equal to 0 if alpha is lower than 1 minus beta and beta otherwise. So again, the result of this integral is an element present in the vector. In this case, we can see that X is eliminated in each focal set of the capacity. There is a value not large enough. And the larger is the value of the capacity, the more permissive is this integrals. So again, I give you a simple example. And this is 0 for the second one, because in the focal set 2, the value is not large enough. So we have both integral with one a maximum and other one with a minimum. In the application, I put in this slide only results concerning this integral based on conjunction, is why it is in second for this presentation. So now I look and go briefly to data presentation. So when you consider a data set, it is important to well choose the model to represent them, because we need to have a good picture of the data set in order to be able to create a good explanation. In this talk, I'm going to consider data sets where attribute domains are on a totally ordered set. And I would like to find a good, appropriate qualitative integrals for a good explanation for this data set. As qualitative integrals are monotonic and increasing, we just consider monotonic classifier. The highest are the value of an element, the highest is the level of its class. When we play with qualitative data and qualitative and monotone classifiers, any class prediction may be justified by one or more rules, satisfy or not, but only based on ordinal information. So we will have select rule. In this case, we give condition for an element to have an evaluation larger than a class given. Elimination rules, we give constraints for elements to obtain in an evaluation less than a given class. And there is a challenge for rules for classifier prediction is because rule sets that are very large with many conditions may be difficult to interpret for user. So I go back to results obtained for Sugeno integral. And when you consider a piece of data made by a vector x and a level alpha, we know the set of the capacity such that the Sugeno integral is equal to alpha. We know that they are between a necessity measure and a possibility measure with a very nice definition because it is simplest one. When you consider an old data set, we need to have this relation for all the level. So we take the maximum of the lower bound and the minimum of the upper bound of the capacity solution. We know we have a characterization to be sure to not have an empty set. Again, we use the Möbius transform of the capacity, and we know that the focal set of the capacity corresponds to selection rules. Focal set of the conjugate capacity corresponds to elimination rules, and there is equivalence with Sugeno integrals and one threshold set of rules. For Gödel integrals, we have not already the same results. I work on it for this time, but I have not, again, it is not finished at all, but I work on this. By now, we know that if Gödel integral based on implication is equal to alpha, we have also a lower bound and upper bound for the capacity solution. And using semi-duality, we obtain also the bound for a conjunction-based Gödel integral equal to a value. And we can extract also selection rules and elimination rules for Gödel integral, but this is not nicer as before because we have just extraction. We have not proof yet the equivalence of this. So to obtain the selection rule, we use the conjunction-based Gödel integrals. And the selection rules is also associated to the focal set of the capacity. And for elimination rules, we use the other one integral with the implication of Gödel, and we use the focal set of the conjugate capacity. we have not equivalent things between Gödel integral and set of rules. We know that we can, if we decide to represent a preference for X and Y, we can prove easily from the lower bound and bottom and upper bound that these elements are not representable by a Gödel integrals. But we know that it is representable by Sugeno integrals. So we know that they are not the same. And we can differentiate them. So I'm working today on this with some co-author, Balu and Kavitz, and we try to find something to apply this for classification. So now I'm going to present you how I can use Gödel integrals for knowledge integration in explainable artificial intelligence. So for this, I use counterfactual examples. Counterfactual examples are popular method used for explanation for prediction performed by a classifier for a data. So they want to answer what I need to modify to get the prediction I want. When you don't have the bus, is not a problem. But when we want to explain why a person is not solvent, we need to explain a prediction offered by a machine learning model in agreement with the users. You can't tell him have one less child. It is not possible. So for counterfactual example, we have a machine learning model and a data instance of interest and a set of counterfactual examples. And we want to choose the counterfactual example to obtain the information about minimal modifications to change the results of the classification. So they are a result of optimization of a cost function, and there are many variety of cost function proposed in the literature. There are many because we need to have a proximity notion. We have to select the criteria. We want to evaluate the quality of the explanation. And sometimes we also need to consider the context. So for Gödel integrals, I decide to use it at the last aggregation. So I consider that I have two criteria, an objective criteria and a subjective criteria. The penalty is an objective criterion, only depends on the machine learning task. And the second one is incompatibility. This is a subjective criterion based on user knowledge. And we want to have small penalty, and we want to have small incompatibility, but it's difficult to obtain both together at some times. So I propose to aggregate them with the Gödel integrals. So why the Gödel integrals? To motivate its application, we need to focus on Gödel integrals considering only two criteria. And in this case, we see that both Gödel integral divide the space in 4 squares. And we want a penalty, yes, a small penalty, and we want a small incompatibility. So we want to be in the left square, and we have two thresholds, one for penalty, one for incompatibility, and we can adjust them with the user and what he wants, what he prefers. So when we don't pass the level for both penalty and incompatibility, we take the minimum. If both penalty and incompatibility pass the level, we take the maximum. And this is the same for both integrals. But if you look at the Gödel conjunction, you see that when you pass the level for penalty and not for incompatibility, we evaluate with the penalty. So we look at what is not good. And for Gödel based on implication, when you pass the level for penalty and you don't want to pass the level, we consider the evaluation based on incompatibility, which is the criterion that is behind the level you want. So I put them together. So Gödel integrals has a good behavior for counterfactual explanation because they have good property. They are non-decreasing in both arguments. Criteria are not equivalent, and they share similar regions and they are similar influence of the parameter on the relative size of the regions. Because for conjunction base, alpha is a level associated to the penalty, but for the implication base, the level is linked to beta, which is the threshold of the incompatibility, but they are both the same. We just have to turn the diagram. Gödel, when the one of the level doesn't pass, no, when we have one criterion that pass the threshold, they have different behavior because the conjunction Gödel is intolerant and the implication is tolerant. Because we think that Gödel conjunctions is intolerant because we are evaluated considering the criteria who pass the level. So since we need to have a small one, we are intolerant because we give bad evaluation. So I have an illustrative example based on half moon dataset. It is a dataset, synthetic dataset classically used for machine learning and classically used with Marie-Jeanne and Christophe. So we have two predicted classes. So in blue and red, we have the training example, the points, and we see the boundary of both. The penalty is just the distance between the cross. The cross is the same intense for all my example. And this is a cross, so the penalty is just the distance between the cross and the other data set, and the other class, sorry. And the incompatibility is all the element in the other class that have the same incompatibility than the cross. So they are a case of Gödel integrals when we put all the weight on the penalty or all the weight in the incompatibility. So I present you variation for alpha and beta. Alpha and beta are parameters in my conjunction-based Gödel integrals. So the first one is alpha equals 0. Alpha is the weight of the penalty. So we decide with alpha equals 0 that we just look at incompatibility. So we have just incompatibility. And on the top of my example, we see that I increase the weight of the penalty. And so we'll look at the green line. This is my selection for counterfactual example. And this green line is smallest. After I present you a compromise, I put some weight, large weight for both penalty and incompatibility. And in this case, we have a sort of compromise to be not far from the cross, but and we need also to have quite proximity with the incompatibility. And the last one, on the right, we put many weights, a large weight for penalty, and in this case, we just have the point that is with a short distance with my cross. So this is a well variation for a good variation for Gödel integrals. So for this part of XAY, I say that I have a user, and with him I try to put alpha and beta from his what he want to have for counterfactual example. And now I'm going to finish presenting you how to elicit Gödel integral in explainable artificial intelligence. So I always want to identify the best counterfactual example. But now I want to identify the best counterfactual candidate even if the user requirements are still not completely unknown. So I will identify the best counterfactual element in under uncertainty context. So I have a set of examples, but in this set, I have no Pareto dominant example, because otherwise there is no problem. I take the Pareto dominant element. So we consider a set of preference for this example epsilon, and we have a set of capacity consistent with this set of example and preferences. So we have to have in mind that I present you before that for Sugeno integrals, we have a set of capacity with lower bound and upper bound, and I up the upper bound and I down the upper bound. And so I have a lattice. And we have also this for Gödel integrals. We have upper bound for capacity and lower bound. So I want to reduce the uncertainty about the capacity playing with my upper bounds to identify an alternative associated with the highest Gödel value for all capacity present in this set of capacity. And this is named the necessary winner for this, and it is a max-min approach. So I know this max-min approach because I work with Paolo Viapiani in Paris, and he proposed this sort of algorithm for Choquet integrals. And many years ago, we decided to try this for Sugeno integrals, and it was okay. And now for this counterfactual example, I try this for Gödel's integral. So I use this just with two criteria because the application is for counterfactual example. And also there are many works to do again next. So I have the set of examples. So they are counterfactual example, and I divide my set of preference in two parts. The first part, I consider elements which are considered bigger than a certain level alpha. And in second part, I consider objects which have got an evaluation, a global evaluation for me lower than lambda. So for the first Gödel integral bigger than alpha, we know that we are created upper bound, no, lower bound, and we take the maximum of these lower bounds. And with the second part of the data set, we define upper bound and we take the minimum of them. And we have also to remind something different from Sugeno and Gödel, is that Sugeno, we can find the global evaluation equal to the capacity. But with Gödel integrals, we always have an element in the vectors. So we first adapt what is explained by user. So I consider 3 examples. And the first one, I consider the preference that its Gödel integral would be bigger than 0.2. We see that 0.2 is the smallest evaluation of A. So as the Gödel integral is like Sugeno between the minimum of the valuation and the maximum of them, with this line, we have no constraints on the capacity. For B, we consider that the global evaluation will be bigger than 0.5. And 0.5 is not present in the valuation of B, so we lead this valuation to Gödel integral of B is 0.7. And we do the same for C because we want this evaluation lower than 0.7. So we lead this to 0.1. Otherwise, it's crazy to try to use Gödel if you don't want to match with the value present in the vector. I identify the capacity, and I have my lower bound and upper bound. So now I have my lower bound and upper bound, and I have no Pareto dominant element. Okay, so I consider the Gödel integral associated to the lower bound because Gödel integral is increasing according to the capacity. And I take the maximum of this. And we obtain what is named the max-min optimal recommendation. After look at this, I consider all the elements different from this element, and I consider the Gödel integral associated to the upper bound. This is the maximum because Gödel is increasing according to the capacity. So in this case, we have the maximal optimal recommendation E0, and this element is the adversary of the first one. And we have proof that if the first one is bigger than the second one, you have a necessary example. So on my example, we have A, B, C, and I compute first the lower bound. So this is the first column associated to Gödel with the lower bound. And the best one is B. So B is E star. And then for the other difference for E stars, I compute the Gödel associated to the upper bound. And we look at the biggest one, and we obtain A. And we have that the evaluation of A is 0.2. This is lower than B. So we know that a star is a necessary example. Again, I have put a picture, and we have, you have the space is divided in 4 squares. So we have this there. In the grid, we have the first capacity, and in blue, we have the second one. You see that my points A, B, C are on the right, and only one criterion is past the level. So, like I am using conjunction-based Gödel integral. I just look for the penalty, and it's okay. My necessary example, which is there, this is penalty, this is incompatibility. He has got the best evaluation for penalty, so it's good. So to conclude, I will speak about my algorithm. So my algorithm, with Christophe Marsala and Marie-Jeanne Lezeau, we name its algorithm Ines. So I'm happy because she's a great researcher, I know, and yes, very nice. So for this algorithm, we start with no knowledge about the capacity. So the bottom is the capacity equal to 0 everywhere, and the top is the capacity equal to 1 everywhere. When we compute the maximum of the capacity associated to the lower bound, we select the max. Then we put away a star and we compute the Gödel integral associated to the upper bound. We select the max. And while we don't have G star bigger than G0, we select a 0 and we take E0. We ask the user if he prefers E0 to be bigger than, to be equal to the minimum of its value, or if he prefers E0 to have an evaluation equal to the maximum of this value. Because we don't have other solution with Gödel integrals. They are just simplest ask. So users say that he prefer one of these evaluation, and we put this evaluation on the algorithm. We update the lower bound and the upper bound of the capacity, and we repeat again to take the maximum, to put it away, to take the maximum, to compare. And okay, I take E0, I ask you a question, and so on. And at the end, we return a star, and we know that a star is a necessary example. So we have proved that this algorithm converge, and we have proved that we never go to empty set because there is a problem with the bounds of the capacity. When you use Sugeno integrals, we always need to be careful to not be on an empty set for your set of capacity. And this is the case with this algorithm. We never go to empty set. So the conclusion of my talk is that I present you a way to use Gödel integrals to stay in a qualitative context from a data set and interpretation, and we elicit capacity. Present you an application to explainable artificial intelligence. I know that I have many works to do now again, because I will try to know if it's possible to use Gödel integrals for more than two criteria? I don't know. We need to do this or to do just classification. I am looking at this for the moment for a binary classification. If I can separate a data set with a Gödel integral, it's a good question. Very interested. And another problem is it's not a problem, is a question. Because if you look careful at the element presence on the lower bound and the upper bounds, we can see that we have the same set that are considered. So they are present for a data set to be representable for a Gödel integral and for Sugeno integrals. So sometimes I think you would be able to use either Sugeno integrals or Gödel integrals. And in this case, the question is, how should we choose which integrals to use for a given data set? So by now, I don't know. Thank you for your attention.
Thank you, Agnes. I'm sure there are plenty of questions, but we start with the first one. Okay, I'll break the ice, and then it will be a second question. In your algorithm where you interact with the user, users are what they are. Like I said, there are no experts. The experts we always use don't exist. So what if in the responses there's a cycle, which is typical in preference? Well, does it then lead to the fact that you have an empty set? Is that one of the cases that could occur?
I know that Christophe and Marie-Jeanne take a lot of time and work many times with other researchers to create questionnaire and to very with the users, they take time to establish what can be here by him. So they adapt for the user.
So the procedure prevents from doing that. Okay.
It is a part of artificial intelligence. It's not for me. It's magic.
Oh, but we have.
But they need times.
Yeah, but magic is specialty here, so
Yeah.
it's no problem. Yes, Andre.
Yes, thank you for the interesting presentation. Yeah, I know a lot of works of Gödel integral of you, but I'm wondering about one, according to me, very unpleasant property of Gödel integral. I mean, in the implication form, if you use Gödel implication, then if you have if you have 0 in the vector, then except the case where the measure of this complement of the set where is the indices and the value of the vector is 0, the Gödel integral always produces zeros. So how do you handle with such situations if you have in application some 0 in the vector?
It's also from I reverse what I want with my application. So if I have 0 in my application, it's the best things I have, because I want to have a small penalty or small incompatibility. So 0 is very nice. So to answer your question, I have turned the problem in this application, and I know that this can't be able, you can't do this in every application. So I know there is a problem with these Gödel integrals.
Thank you.
And yes, it's a very nice remark, because I take in my mind for my future work to make some remarks about this. Yeah, thank you.
Okay. Maybe a last question. I just have a last suggestion. You mentioned at the end to go to classification. There's a setting in between, which also Christophe and I share as an interest, is the one of monotone classification or ordinal regression, where this qualitative thinking is really very interesting. So I would like to see that happening in future talks.
Thank you.
Thank you. So I think we're all waiting for coffee. Let's thank Agnes